Well, good morning, Algebra 2 students. This is Mr. Kingsbury, and it is my pleasure to be walking you through both the exponential and logarithmic properties today. We're going to see how those make things smaller, simplify expressions, or in some cases, how they get a little bit bigger. Before we can simplify and or expand things, though, we need to understand what we're looking at. Let's start with the exponent laws. Now, these are laws you should have seen in Algebra 1. So this first part should be a review. The first one is the zero exponent rule. And by the way, I am not expecting that you're going to remember the names of any of these. I just need you to remember the laws themselves. So the zero exponent rule, it says anything to the zero power is 1. Anything. So for example, 2 to the 0 power, that's 1. 138 to the 0 power, that's 1. 1/2 to the 0 power, that's 1. 2 to the 0 power over 3, that's going to be 1/3, because only the top gets changed to a 1, so be careful. But still, 2 to the 0 is 1. In this case, the 0 only applies to the numerator. In this case, see how I put the parentheses? That means that the 0 applies to the whole thing. Thought you'd want to see that. The second rule, we call it the quotient rule. It has to do with dividing two exponents, two exponential expressions that have the same base. See how it's b in both of these being raised to an exponent? And what we're doing is dividing two expressions with that b base. Well, what the law says is you can simplify that by simply subtracting the exponents, right? For example, if I had x to the 5th over x squared, that would be x to the 3rd. 5 minus 2 is 3. Or if I had, say, x to the 4th over x to the 7th, that would be x to the negative 3rd. We'll talk about negative exponents in a bit. Going the other way, if I had, say, x to the 7 minus 1, then I could rewrite that as x to the 7th over x to the 1st, like so. And you are going to see examples of these throughout our notes and in the practice. The product rule is just the reverse of the quotient rule. This time, instead of dividing the two expressions with the base of b, we're multiplying them. So instead of subtracting the exponents, we will add them. So for example, x to the 3rd times x to the 4th would be x to the 7th. 3 plus 4 is 7. Okay? Q to the 11th times q to the negative 5 would be q to the 6th, because 11 plus negative 5 is 6. And if you had q to the 2 plus 3, you could write that as q squared times q to the 3rd. So this is condensing, this is expanding. Then we have the power rule. Now please be careful. People get the power rule and the product rule mixed up. And honestly, mathematicians do not help that at all, because they named both laws something that starts with P, and both laws have to do with multiplication. So that is a huge problem. The difference is the product rule has to do with multiple expressions. There are at least 2, if not more. The power rule deals with exactly 1 expression. In this case, I have one base being raised to 2 different exponents. In this case, it's 2 completely separate bases. They are the same base, but they appear twice. This one is 1 base. And what it says is you can simplify the exponents by multiplying them. So for example, x squared to the 5th would be x to the 10th. T to the 3rd to the negative 9 would be t to the negative 27. Again, we'll deal with negative exponents in a second. And going in the reverse, if I had, say, t to the 2x, I could write that as t squared to the x. Technically, you could switch the 2 and the x as well if you wanted. Doesn't matter which way you order them. just as long as one's inside the parentheses and one's out like that. And then we have rule number 5. Rule number 5 is a combination of 3 and 4. So, no, I lied. I'm a lying liar. I take that back. Pretend I didn't say that. Number 5 is called the power over product rule. This is when you've got one exponent that applies to a bunch of things. So see here how the A and the B are both inside the parentheses. All of this inside the parentheses is being raised to the M, to the mth power. So what you can do is simply raise each one separately. I like to call this or think of this as distributing, because basically I just gave everything in the parentheses its own exponent, right? So for example, if I have x, y, z raised to the 4th power, that's the same as x to the 4th, y to the 4th, z to the 4th. And the reverse is also true. Let's say that I had a squared, b squared, c squared. Well, I could write that as abc raised to the 2nd power. It works either way. And again, you will see examples of both of these in the notes and in the practice. And then our last one has to do with negative exponents. And there's a long explanation as to why this works, which I'm glad to share with you in class if you'd like, or in tutorials or whatever. But essentially, if you have something raised to a negative exponent, you can get rid of that negative sign by turning it into a fraction and putting it in the bottom of the fraction. And actually, that works in reverse too. So this is really just one direction, right? You have something raised to a negative exponent. Get rid of that negative by basically putting a 1 on it. I like to say put a hat on it. You know, that provides some shade. I don't know. That I may have just taken that metaphor too far. Anyway, let's say that we have, for example, m to the negative 6th. Well, I can make this m to the positive 6th if I put it in the denominator of a fraction. And I'll just put 1 over it. And there are some that get a little more complex than that, but this is the basic of it. The other way that this works is, let's say you have 1 over x to the negative 5th. This is already a fraction, and it has a negative in the denominator. So in this case, you can, and I'm shortcutting this, there's a longer explanation for it, but in this case, if you take it out of the fraction, it becomes positive. So it works both ways. All right, negative outside of a fraction, make it a fraction. Negative inside a fraction, make it not so much a fraction. I will say that when you start to combine all of these, though, the first thing you're going to want to do is combine all of your exponents as much as possible. So I would say, like when I'm working a problem with exponent rules, I always try and use the quotient, product, power, and power over product rules first, and get those things simplified down as much as possible. And once I have only one instance of each variable, then I start applying the negative exponent rule. And sometimes you get lucky and you can use the 0 one as well, because a 0 will pop up. Sometimes you get lucky because you start off with a negative, but because you're combining it with one of these rules, it ends up being not a negative exponent, which is great. So you never know. It's best to simplify those exponents first before you do anything with them. Now, having said that, we have discussed already the idea that exponential functions and logarithmic functions are inverses. One undoes the other. And that holds true for these laws as well. There's not quite as many laws, but they work for logarithms. And I feel like I'm not saying that right, so let me try this again. These exponent rules, we can turn them into logarithm rules by working them backwards, kind of, sort of. For example, you're not going to need the chains of base law, so I'll skip that for now. The quotient property. Remember how we had the quotient rule? It says that you can take a base raised to an exponent that is being divided by the same base raised to another exponent, and you can just subtract them. Well, the logarithm has a similar one right here. It's called the quotient property. They don't have laws so much as they have properties. And what it says is, if you're taking the log of something that's being divided, you can rewrite it as two separate logs that are being subtracted. And the reason you would want to do that is sometimes you get things that are caught inside these parentheses right here. And by being able to expand it out, you can turn some of this stuff into numbers. And the more stuff you have that are just numbers, the more you can combine those, the simpler the whole thing gets. So let me give you an example. Let's say we have the log base 2 of x over 4. That could be rewritten as the log base 2 of x minus the log base 2 of 4. And of course, you can go backwards as well. If I gave you log base 2 of x minus log base 2 of 4, you could write it as log base 2 of x over 4. So it goes both ways. The important part is the bases must be the same. If this was not a 2, or this was not a 2, if these weren't the same, I couldn't use this log. The bases must be the same. Now, we had a product rule up here. Logarithms also have a product rule. And remember, the product rule for exponents was if you're multiplying the two expressions, you can add the exponent. Well, we can do something similar but in reverse for logarithms. If you are multiplying two things that you're taking a log of, you can rewrite them as two separate expressions being added. So say the log base 5 of 7x, that could be written as the log base 5 of 7 plus the log base 5 of x. And again, it could go the reverse as well. I'm writing it in an expanding way. So I start with something smaller and it's getting bigger. 1 log, now it's 2 log. But you can go the other way, which I'll show you on the other side. Let me do some examples. Power property. This one goes along with the power rule. Remember here, if you're raising a base to two separate exponents, you can just multiply the exponents. Well, the power property here for logarithms works similarly. Only this time we're taking the log of something being raised to a power. And what we can do, this is very interesting, is instead of having it as an exponent, it turns out you can move the exponent in front of the log and multiply by it. That is huge, because that is a way to turn an exponent into a coefficient, which is much easier to cancel out. You don't have to use any square roots or cube roots or any other roots. Crazy. So for example, let's say we have the log base 9. That's a 9. Didn't look like a 9. Of, let's say, n to the 5th power. I can write that as 5 times the log base 9 of n. And I can go in reverse as well, which you may want to do. The reason we find these properties is because when we're solving stuff, it can help us to rearrange what the equation looks like. When you do that, it allows us, again, to turn things into numbers. Next time, we will talk about how to use these properties to solve equations. And when we do, you will see that being able to turn the equations, to change the equations into something that looks a little different, really allows us to turn a bunch of things into a single number, which is going to be really, really, really cool. The second to last one here is called the equality rule, what I like to call the duh rule. If you have a log with this certain base of something, and it equals the log of something else with the same base, then the two things in the parentheses are equal, right? You're taking the log of both of them. It's the same base, so what's in the parentheses must be the same. Let me give you an example. Let's say the log base 3 of x equals the log base 3 of 10. That means, or that would imply, that x equals 10. This is a great law because it lets you get rid of all this extra stuff. You don't have to deal with logarithms or bother undoing them because you know what's inside will be equal. Look at that. I got a nice, I actually solved that. X equals 10. Done. The last thing here is called the change of base formula. And at one point we needed this. This was important. Now that we have calculators that have commands that let us take the log of any base, we don't need these so much, which is great. What it says is if you want to change your logarithm with a base of a to some other base, you can take the log in the new base of what's in the parentheses and divide it by the log of the new base of the old base. And I'm sorry, but this bothers me. I'm going to put a little b here and here. because right now it was specific to 10, to the base being 10, and I want it to be any. Let me see if I can give you an example. Let's say that I have the log base 7 of 16. Let's say for whatever reason I want to change that to be in the log base 5. So what I'm going to do is take the log base 5 of 16, the part in the parentheses, and then take the log base 5 of the old base, which is 7. Mostly this is important because for a long time, our calculators could only take logs in base 10. So when we were typing it in, we had to change everything to base 10. And we needed this to do that. So once we got the equation mostly solved, then we would have to change the base so that we could actually type it in the calculator. You will not use this law at all. You will use these 4. But we wanted you to see that because it's important. Now, let's do some problems. I've got like 16 of them. They don't take very long at all. So I'm going to blow through them right here. The directions say simplify or expand. So if it's simplified, we're going to expand it. If it's expanded, we're going to simplify it. First one here, we get the log base 3 of 9x. Well, there's one there that there's a log property that says I can rewrite this as 2 separate logs. And since they're being multiplied, all I have to do is add them. Number 2 is very similar. There's a law that says since I'm dividing these two things, I can write them as 2 separate logs. The top goes first. It must go first. Honestly, up here, it's not that big a deal because it's addition and multiplication, which are what we call commutative. It means you can write them in any order. Division and subtraction are not. This is division. So you must write the top one first, and then the log base 2 of 4. And then because it's division here, we can write it this way as long as we subtract. No big deal. Number 3, the natural log of 3 to the 7th. Don't worry that this is the natural log. That's just a log base e. We talked about e last time, and that it's a special number in a special case. In this case, all we're going to do is move this exponent in front. So we get 7 times the natural log of 3. No big deal. I like this one because it's going to use 2. Oh, this is going to be awesome. X to the 4th over x to the 4th, right? Well, we would write that as x to the 4 minus 4, right? We have an exponent law that says you can subtract these, but look what 4 minus 4 is. It's 0, and we have another law that says anything to the 0 power is 1. That worked out beautifully. I love it. Amazing. Number 5, we've got 9 to the 2x. I got to be honest, the first time I looked at this one, I was like, I'm not sure what to do there. But remember, we have a law that says if you're raising one base to 2 separate exponents, then you can multiply those exponents. That's what we're doing here. We've multiplied the 2 exponents. So I'm going to write this as 9 squared to the x power. You could write it 9 to the x power squared. That's fine. It doesn't matter. I did it this way just because 2 comes first and x comes second. Not a problem. Number 6, this one's going to get a little difficult. Not terribly, but we're going to break it into 2 pieces. So first, we have this 5, this exponent of 5, that's being applied to everything in this set of parentheses here. And then it's all inside the logarithm parentheses. So first, I'm going to move the 5 in front of the log. So I get 5 times the log base 2 of 3 divided by x. Then the second thing I'm going to do is like I did up here on number 2, and I'm going to write 2 separate logarithms, one for each piece. So I've got 5 times the logarithm base 2 of 3, and 5 times the log base 2 of x. Now because the 5 is outside the log, before we start splitting it up, I'm including it on both of them. And since this is division, I'm allowed to write it this way as long as I subtract. So this will be my answer right here. That's what we call the expanded version. The 5 had to be included in both because it was there outside before we split the log into 2 separate logs. This next one you're going to see, I'm going to do it a little different. Please note that in this one, yes, there's an exponent and there's 2 terms, but this exponent only applies to the x. If there are parentheses around the 3x, I would handle it much like I did up here, and I would move the exponent first. But in this case, it only applies to the x. So before I can move it, I need to split these two up. So I'm going to write this as the log of 3 and the log of x squared. And I can add them since it's multiplication. I can add them. The log of 3 is not going to change at all. There's nothing more I can do there. But I can take this 2 and put it in front of the log here. So log of 3 plus 2 times the log of x. And again, I had to do it that way because the 2, the exponent, only applied to one of the terms in my parentheses. On number 6, it applied to everything in the parentheses. On number 7, only to the x. So I had to split those up first before I could do anything with them. Number 8. We've got 5 times the log of 2 equals the log of x. So I'm seeing that we have a 5 outside. I'm going to go ahead and move it back inside. This is one where we are condensing. So this will be the log of 2 to the 5th equals the log of x. And now I can use my equality property, which says if I'm taking the log of two different things and it has the same base and they are equal, then the stuff in the parentheses, that is 2 to the 5th and x, they are equal. And you're welcome to leave it right there. Mathematicians would generally encourage you to go ahead, that was wrong, to go ahead and expand this or evaluate this. 2 to the 5th is actually not 25. It's 32. So I would take either of these. So whichever one works for you is fine. Halfway done. I don't want to go too fast, but these are pretty quick. 2 to the 3rd squared. So our law says we can multiply those. So this is 2 to the 6th. And if you want to evaluate it, you can write 64. That works as well. I'm looking for this. That's fine. Let's see. I think we've done one with the 0 in it, but we know what 2,378 to the 0 power is. It's just 1. Number 11, we have our logarithm rule where we're subtracting. This time, though, I'm going to condense, right? I did one over here, number 2, where I expanded. Okay, it was two things being divided, and I wrote them out separate. Well, this is what we're being given now. I've got two things. They're being subtracted. They do both have a base of 2. So I can rewrite this as 1 log with a base of 2. And because it's subtraction, I'll just use that subtraction as a division sign. The one in the first parentheses goes on top. The one in the second parentheses goes on bottom, excuse me. And yes, it is absolutely imperative that you write it like that. You can't put the 12 on the top and the x on the bottom. Must be written this way. Whatever comes first here goes on top here. Number 12, we've got an x squared and a y squared. Both of them are being raised to the square. So I'm just going to, if you will, factor it out. Really, remember I like to call that distributing when we talked about that rule. Each one gets one. Well, going the other way, it's kind of like factoring it out a little bit. Number 13 is a lot like number 8. Once we did our first move there, we've got log base 2 of x equals log base 2 of 9. They're both logs with bases of 2. That means x equals 9, which is awesome. I got to be honest, I'm going to do this one way, but it's not how I would handle it. This is all numbers. So if it was me, I would make this 81, call it 1 over 81, and everything's good. But what they want me to do, what I'm supposed to do is remind you that when you have a situation like this, you can rewrite it as 9 to the negative 2 power if you like. That might come in handy. I don't know, but that's what they're wanting you to do, is point out that 1 over 9 squared started out as 9 to the negative 2. Number 15, we're dividing two exponential expressions that both have a base of x. What we can do is subtract, right? So this becomes x to the negative 3 minus 4, which is x to the negative 7. And then if you recall, we were just talking about this up here. We went in the reverse of what we're going to do here. I can make this not negative by putting a 1 over it. Think of this as a ray of sunshine, this little negative, and putting a hat on it keeps the ray out of x's face. I don't know. I'm reaching there. Let's see. And then lastly, we have number 16. So we got negative 3 times the log of z. We certainly have a log property that says we can move this negative 3 inside the parentheses and make it an exponent. So the log of z to the negative 3. But also, if you recall from our previous problem, we don't like negative exponents. So we can make this not a negative exponent by making it a fraction. So we'll go 1 over z cubed. So the log of 1 over, the log of z to the, holy guacamole, the log of z to the 1/3 power. I'm not saying English right. Anyway, those are the laws and the properties. You're going to see a lot of them. I think you're going to find that using them allows you to solve quickly and easily. And thanks for your attention. I'll see you in class.